All right, let's take a little breather in order to introduce the next two talks. In the first talk, we will have Peter from Sisu in Stanford address the topic of high cardinality analytics. This will be followed by Dan from Google, who will explore how Spanner uses globally synchronized time to achieve consistency. Enjoy the talks and see you right after for the Q&A.
Hey, my name is Peter Ballis. I'm coming to you live from the San Francisco Bay Area, and I'm excited to talk today about how we can use ideas from distributed systems to enable scalable, high-dimensional analytics with mergeable summaries. The high-level idea behind this talk is that we can take ideas from distributed computing, specifically around reconciling distributed state, and apply them to really high-dimensional analytics, especially in a distributed environment where events may be arriving late, and we certainly can't store all of our data. So I first came across this problem as a researcher. I spent my whole PhD dissertation working on reconciling distributed updates, and very quickly got excited about a lot of the work going on in streaming and event-based systems. And eventually this took me even away from campus, where today I spend all my time at a startup. But a lot of the ideas I learned as a grad student and then early faculty member back at Stanford apply to this scenario and have proven really, really useful both at our scale and at Microsoft Facebook scale. So we're going to take an idea that many of you have likely seen time and again, which is how do we reconcile distributed updates to state, and we're going to apply it to analytics. So perennial problem, distributed systems 101. What do I do if I got different servers and updates go into those different servers? And how do I make sure that I get the right results back when I actually query my data? And the idea is we get 1 + 1 = 2 by designing the right data structures and ways to combine these data structures in order to ensure that the right thing happens. Specifically in distributed systems and eventually consistent systems, we make sure that our merge operations for combining data structures are commutative and associative. So no matter what order they come in, I can actually make sure that the result is still the same. And many of you may have seen these ideas first in some really interesting pioneering work from Mark Shapiro's group out of INRIA in the form of these CRDT data structures, so commutative and replicated data types. And what CRDTs are, and if you've used CRDTs, essentially a library of really useful data types for counters and sets and maps that let you add and remove and subtract a bunch of different items and you get the right results. Why? Because you're using commutative and replicated merge operations. So this talk's not about CRDTs, but it's about the surprising connection to analytics that at least I found super interesting when I was facing some of these problems, specifically on how we can use commutative and replicated merge operations in order to go and get the right answer out at high scale, high speed, and high accuracy at really large web scale. Started this as research at Stanford. We've deployed it at Sisu. A lot of our research is actually done in conjunction with some teams at Microsoft we'll talk about, and some of it's even landed in open source in the Apache Druid project. So let's jump right in and imagine you're operating a large internet service like many of you probably are. If you release a new application and you want to understand what was the impact on tail latency during the last release window on a bunch of devices, let's say non-Apple device in the US, you suddenly have a high-dimensional analytics problem on your hands. Each event you're collecting, whether that's from servers or from phones or from applications you've deployed, likely has a bunch of different attributes or dimensions hanging off of it. And the challenge you're going to face is how do I go and efficiently query the dimensions I need out of the hundreds of dimensions that might be relevant to my data? And how do I do this in a way that's super efficient without storing all this data? So I don't want to keep all my raw data around. It can grow insanely large, especially at scale. I don't want to go query it all. It's too expensive to run MapReduce or Spark jobs and just scan it. And then ideally in a distributed environment, I don't want to even centralize all this data or wait for all of it to arrive. How do I get queries over the best data I've got at each point in time? And the surprising trick that we're going to talk about in this talk is there's a class of data structures that leverage this idea of merging in commutative and associative ways that can go and address this in the form of these mergeable summaries. Now, before we jump into mergeable summaries, there's a really useful data model we're going to use, which also corresponds to a system architecture that's very, very common at scale, both in systems like Druid, but also in a lot of these systems that you've seen in OLAP querying, either used as a cloud service or maybe have used internally at your companies. And that's the idea of a data cube. So quick refresher, what's a data cube? It's a way to visualize and to store data that is high dimensional. So I've got these 3 dimensions here: model, country, hour of day. I've got a data cube. I lay out each of these dimensions and each of the values of these dimensions as different rows and columns and slices of the cube. And this abstraction breaks down. Blame Jim Gray, who came up with this stuff in 1995. With n dimensions, so more than 3 dimensions, you can visualize a hypercube, or you can just imagine this thing going out into an infinite number of dimensions. But it's a useful primitive for indexing our data. Specifically, if I want to go query all the Galaxy S20 devices, super simple. Go find all the Galaxy S20 devices, find that row, find the slice corresponding to 5 p.m. Boom, there I've got it. Just got to go access the data in this cell. If I want to go find the users who aren't in the US, simple, take the complement of the USA slice, get all my records, good to go. So a very simple way to kind of visualize and store my data. And I can actually lay out my data in a cube as well. And the key trick, and this is classic dating back to the early days of data cubes, is you don't want to store the raw data in the cube because it can be really expensive, right? And you want to store multiple copies of the data if an individual data item appears in both the USA cube and in the Galaxy S20 cube. And so what we're going to store instead are these kind of aggregates or summaries of our data instead. And classically, we stored things like count and min and max and sum and average. And those are super useful. They can answer a ton of classic analytics queries, but they're not going to answer the questions we want to answer in this talk, which is how do I do things like top K and percentiles and distinct items? And what if I want to run arbitrary functions over all my data? So the trick here is how do we design summaries that can let us do really interesting queries and the types of queries we want to run at large scale over interesting, complex online cloud applications like many of us operate today. Well, with this data cube framework in mind, we're going to have a pretty basic architecture. We're going to basically have devices, whether not they're phones or servers or otherwise, go and send the raw data up to the cloud, or they can even aggregate it on the device. But regardless of how we do this, these folks are going to send the data to what I call a pre-aggregation service. So there'll be a service in our environment going possibly within the database, collecting all this data that comes in and aggregating it. So if an item comes in for USA and Galaxy S20, we go aggregate that with all the other events that came in for USA and Galaxy S20. And over time, we'll accumulate updates that we want to apply to our main data. And with these updates, which are basically like mini cube cells we'll be sending over as summaries, we'll go and apply them to our overall cube that we've pre-materialized. So if you're familiar with materialized views, the cube's like a giant pre-materialized view. And the benefit of this is that we can query the cube instead of querying the raw data. So we don't have to scan anything. We just go find the cube cells we want to go look at, and we're done. Now, this is all well and good from a conceptual perspective, but the hard part is how do we tailor our summary data structures? How do we actually decide what goes in each and every one of these summary items and goes in each and every cell in the cube in order to actually balance efficiency and accuracy? If we can't store all of our data, what should we store? What data structure should we use? Well, this is where this idea of mergeable summaries come in, which is a super useful primitive. And our goal is to introduce these mergeable summaries and then talk through some useful examples so you can kind of demystify how this stuff actually works. So, define these mergeable summaries. I want to first and foremost state for really big data, you can't store all the data. You're only going to have to store, say, an approximation of the data. So our mergeable summaries are going to be in the context of an approximate answer to all of our queries. And it's basically a form of lossy compression. So you're all familiar with the idea that, with JPEG compression and images, I can make my JPEG smaller by degrading the quality of my image. We're going to do something similar here, but we're not going to look at pixels. We're going to look at classic data structures and how we can truncate them and chop them off and use counters and sets and so on in an approximate way in order to answer the queries we want. So with this idea of an approximation, the idea of a mergeable summary is really simple. A mergeable summary is a summary of a data set that, upon merge with another summary of the data set, preserves both accuracy and size. So if I've got, for example, two different data sets, right? I've got this red one here, and I've got this white one here. I should be able to compute a mergeable summary for each of these. Let's say summary on the left's got 1% error and 1 kilobyte worth of space. The one on the right's got 1% error and 1 kilobyte worth of space for the queries I want to run over it. This summary is mergeable if and only if I can combine these two summaries with a merge operation and get out a combined summary that is the same size and same error as the individual data sets, as the individual summaries. And the thing that's really hard about this is that that bottom summary has to be as accurate as if you constructed the summary on the entire data set, red and white combined. And the hard part here is I have to bound the accuracy. I can't just have errors accumulate. 1% error on one data set plus 1% error on another data set can't give me 2% error. I want to get 1% error or better as I merge. That's pretty hard to guarantee, and that's what we're spending a lot of time talking about. Now, once I've got these mergeable summaries, life is really, really good. So at ingest time, I compute the summaries for the appropriate part of the cube, and then whenever new data arrives, I just merge it into the existing cube cells. So I can literally ingest data all day, applying merge, 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 and my accuracy stays the same. We can possibly even get better, but probably just going to stay the same. And then at query time, I go query the appropriate cube cells. I can merge them all together. I get one summary out, which is the summary of all of the data that I had to go and query, and I just go query that summary cell. So it's very small, very efficient. And with this architecture, we address a lot of our challenges we started off this talk with. So we don't have to store all the data because by construction, these summaries are bounded size. We don't have to query all the data because we just merge the summaries related to whatever query we wanted to run. We don't have to centralize the data because each node can compute its own mergeable summaries and can merge it later. It's associative and commutative. It doesn't matter what node computes what summary as long as the data eventually arrives. And if the data arrives out of order, this is also pretty awesome because, again, it's order insensitive. So if a data point arrives late, or say one of my phones is delayed in terms of reporting because it's offline in airplane mode, I can still go and get that data and merge it in whenever I want. And this is all pretty exciting, but especially for those of you familiar with CRDTs, the hard part is what's in the summary. So with CRDTs, each type of query, whether or not it's doing a counter or a set or a map, requires its own summary data structures. There's a whole bunch of these, a whole family, like a library you could think of it as. And the question for us is, what the library look like for mergeable summaries, and what types of queries can we even answer in a mergeable way? Right? It's really, really hard, as we'll see, to guarantee both bounded size and bounded accuracy and provide accuracy guarantees so errors don't compound and blow up. And a lot of the conventional summaries you may have seen in terms of sketches, they can blow up in terms of accuracy if you aren't, thoughtful about this. This is why this whole field started back in 2012 when people realized just doing the normal stuff is going to lead to errors that compound over time. And as we'll see later in terms of production services, if you're running thousands, tens of thousands of merges on an individual query, those errors will compound and will impact end user quality. So what do these look like? What are some useful summaries? Well, let's take a quick tour of some of my favorites. First one, this is probably my favorite summary in that it's really simple, but actually surprisingly effective. So query type we want to support is top K. So what are the top 10 most common users who logged in the most over this period of time or over this, let's say for this type of device and so on. Hard part with this, if you just do a little, mental math, if I have a service like Facebook, there's billions of users. How do I avoid storing billions of different data points in this particular summary? Well, we're going to consider a really simple proposal, which is let's just store a hash map of the most common items. And then to keep that hash map bounded size, whenever we merge two maps, we'll add together the contents whenever there's a match, and we'll drop anything that's not the top K. So quick example of this. Let's say we have a top K and we want to store a hash map of size 3. So our summary is maximum size 3 elements. We've got a summary from one data set, Superman, Batman, Hulk, and then another data set has Superman, Joker, Robin. If I combine these two hash maps, what I'm going to do is I'm going to add together the common elements, which in this case is just Superman. And then Joker and Robin, or so Joker and Batman are the next two most popular items. And then Robin and Hulk are not in the top 3, so I just drop them. I drop them from my data. So I'm basically just adding in more and more hash maps and combining them and only storing the most common elements that we see. Now, this is a pretty simple idea, but the shocker here is it actually works pretty well. So there's some math here, but you can show that with 100 elements in this hash map, you can guarantee the count of any item in the data set with error at most 1%. And for many elements, it can be a lot better than that, but this is like worst case error. And with 1,000 elements in the hash map, which is still pretty small when you think about the amount of data that you can store on a modern server, you get 0.1% error. And the error basically scales with 1 over epsilon. So if you have a summary of size 1 over epsilon, you get epsilon relative error. And if you read the original Mergeable Summaries paper, which I'll link to at the end of the talk, this is actually optimal for this problem, which is kind of a shocker. It's not an intuitive algorithm that you have to drop things from the hash map, but it's pretty surprising that this works so well. And you can answer now these top K queries over arbitrarily sized elements, an arbitrary number of dimensions, really, really efficiently. And if you implement this with a fixed size array instead of doing it with a linked list, in terms of your data structures, you can also do this really, really efficiently. All right, so let's look at a different type of query. Let's look at percentiles, or what's called quantile estimates in the literature. And what these quantile estimates will let us do is answer questions like, what percentage of users have latency less than 10 milliseconds? So, for example, if we store percentile bins of different data sets, let's say we compute the median, the 75th percentile, and 99th percentile of our data sets, we can answer some of these queries really well. So I can tell from the example on the right that half of my users had latency less than 1 millisecond. But if I get my bins wrong, I stored, say, the 99th percentile for summary A, and that tells me that 99% of the users in dataset A had latency less than 10. But I store my bins for B, and all I have is 1, 100, and 1,000. I have no idea if it's 50% of users that had latency less than 10 for summary B, or if it's 75, or 73, or 72. I've kind of lost precision when I look at these data sets when they're combined, because I would have drawn the bin boundaries differently if I had access to both A and B in terms of the raw data. And when I merge these, I have no way to combine these in a way that doesn't lose information. So specifically, because these percentiles may not align, it's a lossy merge operation, and the summary is actually not mergeable. So we came to this problem actually working with a really large production deployment at Microsoft, looking at things like Microsoft Skype, call quality, and latency. And my student Edward, who's working with this team at the time, had a really clever idea to solve this problem. So specifically, Edward realized instead of trying to compute the percentile bins, what if we computed way simpler statistics about these data sets? And then at query time, we're able to somehow reconstruct the distribution and query that distribution itself. So don't store the distribution, but store some statistics that could be easily merged and then later queried with a more expensive routine. And Edward's proposal looks like the following. We're going to store some really simple statistics. You use these same statistics in CRDTs: min, max, count, sum of x squared, sum of x cubed. We take some logs of some of our data. But basically, really simple statistics that are easy to compute. And it turns out that with these really simple statistics, they are sufficient in many cases to go and reconstruct that actual distribution. So we can use a numerical solver and numerical optimization routines to go and reconstruct the true distribution from these statistics, which are known in stats as the statistical moments of the distribution. And what we're essentially doing is we have this really fast array-based operation over the individual moments. And then at query time, once we've merged, say, hundreds or thousands of these different sketches together, we can go and pay the cost of running a solver once. And this works out really, really well. Just to illustrate what it looks like from an actual example worked out, if we just store the first two moments, you've got min, max, count, and then the sum of x and sum of x squared. Obviously, sums of operations are commutative and associative. Min, max, and count are commutative and associative as well. So this data structure is in fact commutative and associative. We get the same result merging the data structures if we had queried it, as if we had constructed it over the red and the white data set independently. And it ends up being both super efficient and very accurate for many of our distributions. So in this case, we have a really complex numerical solver routine reflecting the statistical guarantees we're trying to provide from this sketch. But the actual data structure itself is super easy to code up. You can code it up in like 10 lines of code. And there's a bunch of other alternative, more complex data structures. But for us, this was especially important because you have linear time updates, and you don't have to maintain any complex tree or dynamic programming or any of these, relatively complex algorithms that you can find in the literature. Now, natural question you might ask yourself is, what if there's no known mergeable summary for the function I want to run? Let's say someone gives you a user-defined function, or you want to run arbitrary, say PL SQL, or you want to do some complex calculation for which there isn't a simple known mergeable summary. Well, rather than throwing up your hands, it's actually possible to go and address this problem with a relatively simple trick. It's not elegant. Stats folks in this call are going to cringe, but it turns out that maintaining a uniform sample over my data for each cube cell is actually mergeable. Because when I merge different data sets together, I can essentially resample my sample based on the frequency of occurrence and so on. And so basically by maintaining keeping a small amount of data, let's say 1,000 items or 10,000 items, even 100,000 items in each cube cell, I can then go and run arbitrary computations over that. And I can merge the data sets that I need, or the cube cells I need to, in order to go and run my complex function. And if I'm smart, I can use things like holdout sets or bootstrapping and so on to make sure I'm getting a good guarantee from this result. It's not going to be as good as if I had a tailored sketch or a tailored summary, but I can run arbitrary functions. So we use this trick in an earlier stream processor we built on campus where you wanted to run arbitrary functions to classify elements of a stream. And we used this stream reservoir, which we would merge over time across different cells, to basically go and periodically retrain models. And we actually used another reservoir, another sample of the stream, which was appropriately weighted, to go and check the accuracy of this. And so if it drifted too far, we'd go and recompact all of our incoming reservoirs, retrain the model, redeploy it, so on. And I just want to call this out because you won't find this in literature, but it is true that a uniform sample is resamplable and really useful if you practically want to run a function over your data and you have this high dimensional slice and dice problem. Works relatively well. Your mileage may vary based on how big it is and what function you want to run, but very practical, useful trick. Some might call it a hack. So in summary, there's a bunch of useful mergeable summaries. We didn't talk about things like distinct elements, but there's well-known approaches for those. The idea here is the more data you can allocate, the more storage you can allocate to these summaries, the better they get. And there's a lot of work trying to get these error bounds further and further down using more and more complex algorithms. But the stuff actually works, and you can answer a bunch more interesting queries than average and max using these mergeable summaries, specifically leveraging this idea of a merge operator from distributed systems. Not sure that's where the mergeable summaries authors got the inspiration, but when I saw this, I said, this looks like a CRDT, but for statistical queries. So the best part of these summaries, they actually work in practice, and especially work well at scale. So to leave you with a few lessons from actually productionizing these types of sketches and summaries, draw on a couple of our experiences deploying these. So first and foremost, when we worked with the Microsoft Skype team and looked at the distribution of their queries, as in this VLDB paper from last year that I mentioned, they merge a lot of different summaries at once, up to thousands, tens of thousands, and in the median, 50th percentile, they merge 100 summaries per query. So this means that the types of optimizations like in the moment sketch to optimize for fast merge times and possibly slower query times actually pay off, especially when you have super high dimensional data. Second thing we notice is that a lot of times cells are queried together. So I'm going to query some dimensions way more often than others. And I'm rarely going to query the individual cells on their own. And with that observation, we can actually bias our summaries to give you better global error at the cost of reducing quality for individual cells. So for example, if I go and store just the top element for all of these individual cells, where I've got 51% A's, 49% B's, my accuracy for A's are great. Accuracy for B's, terrible. Could be B, could be C, could be E, not going to work out very well. But if I know I'm going to query all these cells together, I can actually sacrifice the accuracy of some of my cells and store B's in some cells and A's in other cells. And by leveraging some ideas from this crazy theory called discrepancy theory, I can actually get better overall error by sacrificing the individual summary accuracy as well. It just comes down to how I compute these summaries and how I track bias over time. And finally, there's a lot of math in this talk, probably more than any other in this conference, at least this year. But the nice thing is this stuff actually works really well. And for example, in the Druid engine, we see at least 5x speed up for relatively merge heavy queries. And that difference between, say, 12 seconds and 2 seconds is the difference between sitting and twiddling your thumbs and a user getting bored, and then a user staying super engaged and be able to drill down. And we found these ideas super useful, not just at, say, Facebook scale, but also when we look at data inside of modern direct-to-consumer companies, B2B SaaS companies. We see this type of speed up helping users out all the time, especially in our work at Sisu, where we're building this online analytics platform. These ability to slice and dice quickly really makes the difference in terms of user experience. So in summary, these mergeable summaries are really useful. They take the idea of merging from distributed systems and apply it to the statistical context. Super useful in terms of bounding both efficiency and accuracy and getting great results out. And they've proven useful at FANG scale and at startup scale. And the really exciting thing is that this field continues to evolve super fast. We're only about 8 years in since the initial paper on mergeable summaries, and there's new results every single year. I'd be remiss if I didn't thank the original creators of mergeable summaries, really visionary work back in 2012, and a bunch of collaborators who have worked on various pieces of the work I talked about here as well. If you're interested in learning more, there's a bunch of great work, including Edward's whole PhD thesis, which puts this in a very practical context, in addition to the original mergeable summaries papers, which are very approachable and also really fun to read. So I appreciate your time, really, really grateful for the opportunity to come speak and would love to take questions.